All right, so good afternoon, everyone. Oh, you know what? I don't think I'm sharing my screen yet. So let me share that. All right. I think now you should be able to see my screen in Tifton, right? All right. Okay, so I just I just noticed I don't think I emailed the class asking you to download the material from GitHub. Um, But if you can go ahead and do that. So just like you downloaded the first time, you can download again. If you want, so let me show you something here. So I'm gonna go to the folder of the course on my side. So this is what it looks like on my side for now. There's the 01 intro. You probably have a 2025 PPA main if you download it from GitHub, and then I have an extra folder. If you remember, I asked you that on the 2025 PPA main, if you want, you can really just delete the current version you have, and that should not be a problem. And the reason for that is remember that on this folder, once you download it from GitHub, those files are just I'm just using GitHub to share the files with you, meaning that I do not want you to be coding from the files that come through 2025 PPA main. I want you to copy those files from there, paste them into your folder, which we created the 01 intro last time, and then work with that file instead, not the one that is still on 2025 PPA, right? So if you did that, you could have simply, if you wanted, you could just delete 2025 PPA main that you have currently, and then just download the new version, which has the same files as before, plus a few new files that I uploaded for today's exercise. Anyways, that's just an advice. You do as you wish. If you want to keep all copies of 2025 PPA main as you download them, you can do that as well. Um, but anyways, please go ahead and go to the GitHub repo of our class. We have the links for that in the website. I do recommend you bookmark them because we're going to be using those links a lot. And once you're there, I want you to download the repo as you've done the first time around. So let me show you on my side here. If I were to do that, I would go github.com/leoambastos/2025_PPA. And then you click on this code button and download zip. That's what we're doing. And if you want to, once you download that zip, if you want to move it to your, let me see, to the main folder of this course, you can do that as we were just talking about. All right, so a couple things that we're going to do today. We're going to be introducing a few different concepts all at once, and but they happen in sequence that I hope makes sense for you to understand. So our next exercise here is going to be a data wrangling exercise. Data wrangling is basically a term that's used to refer to when we are manipulating data, and not in a bad way, not manipulating in the way of like I'm making up data or I'm deleting data or making up data, not that. Manipulating data in the sense of, we're going to clean this data, we're going to create some new columns that we need to create, we're going to reformat the shape of this file, we're going to filter out some rows, and so on. So data wrangling is, in every project that you have data wrangling is probably going to be anywhere between 25 and 75% of the work, depending on how much it requires. So it's really a really important, I guess, topic to learn and tool to be able to learn how to manage data in different ways. And we're gonna start doing that in R today with this exercise. But just to let you know, we're gonna continue doing this every single time we have data. We're always gonna have data wrangling. Today is just an introduction to data wrangling, so you can get familiarized with some of the most important functions that we're going to be using. All right. After having said all that, we're going to create, if you are here on the main folder of the course, and you're seeing something similar to me, I'm gonna come here and create a new folder that I wanna call 02 wrangling. Right, so this is gonna be our second exercise. Notice how as we develop things in sequence, we're gonna be creating this structure here of naming 01, 02, 03, all the way through our last exercise, the last day of class. And so things remain organized. Now, if you come inside of 02 wrangling, which you just created, it did not come from GitHub, you just created on your computer, go inside that folder. So now you are inside 02 wrangling, and I want to introduce you to the way that we're going to organize our files from this point on. Every time you're working with data that's related to, it could be maybe related, in this class, it's going to be related to each topic we're covering, but this concept here, I would highly recommend you implement on your own research if you have not done something similar yet, just to keep things organized, which is going to be two main concepts. The first one is we're going to create a structure of subfolders where we're going to save files that are specific to that type. For example, here inside of 02 wrangling, I want to create a folder for data. So all data files that we have associated with this exercise, 02 wrangling, are going to go inside of this data folder. We're going to have another folder for code. This folder normally can be called like code, scripts, markdown, quarto, whatever it is that relates to coding or to the script itself. And the last subfolder is going to be called output. So this folder is where we're going to save any plots, any maps, any tables that we create as outputs of our analysis. This way we keep things organized. Each file has their own subfolder inside of this project. Another concept here is these three subfolders, data, code, and outputs, are the minimum that we're going to have in a project. You could have more than this, so sometimes if the project that I have the analysis is also where I have the manuscript I'm writing for that analysis, I may have here a folder called writing. Or maybe if I have other PDFs or tutorials of things that make sense for this project, I may have another subfolder called resources, right? So this is very flexible, but it's just a minimum structure that I would recommend you implement for your research, and that's something that we're definitely going to be doing throughout this class from today on. All right, so code, data, and outputs. So what I want you to do now is, so I'm going to go back one level and be at the main level of the class. I want to go inside of 2025 PPA on your side. It's going to be 2025 PPA main. So go inside of that folder. And assuming you have downloaded the newest version that I uploaded maybe like an hour ago or so, and you have just downloaded that in class, if you go inside of the folder 03 data, so I am inside 2025 PPA, I go inside 03 data, there is a data set there called 01 soybeans, okay? You should be seeing this on your side from the version you just downloaded from GitHub. If you are not seeing, let me know, but it should be seen. So let's copy. So remember, we are just going to 2025 PPA to copy the files from there and then paste them inside of our own folders. We're not using them directly straight out of 2025 PPA. So copy the 01 soybeans, go back one level, go back another level. You should be back at the main level of the course. Now go inside 02 wrangling, go inside data, and paste it. So you should have 01 soybeans.xlsx inside of the data folder, which is inside 02 wrangling. All right. Next, we're going to do the same thing, but for the script. So I am in 02 wrangling right now. I'm going to go back one level. I am at the main folder of this course. I go inside 2025 PPA. I go inside 04 class code, and you're going to see that there is a new script there that's 0114 data wrangling partial. I want you to copy that script from the 2025 PPA, go back one level, go back another level. You should be back to the class main page. Go inside 02 wrangling, go inside code, and paste this code. All right. So again, we're just copying files that we downloaded that are inside the 2025 PPA and then pasting them into our own working directory, which is 02 wrangling, right? I do not want you to just be using the files straight out of 2025 PPA and working on those versions. That's not what I want. I want you to be able to delete 2025 PPA and not miss anything, because you're actually copying files from there and pasting in your current version of that script, which is inside 02 wrangling. So before we keep going, I'm just expanding my tabs here. So this is how your 02 wrangling should look like. You should have, so on the main folder of this class on your computer, you should have a folder called 02 wrangling. Inside of 02 wrangling, you should have a folder called code, where you have copied the script 0114 data wrangling partial. You should have a subfolder called data, inside which you copied, or sorry, you pasted the 01 soybeans Excel file. And then for now, output is empty. You don't need, this is something we're going to create maybe at the end of the exercise. This is what it should be looking like. It should be looking like on your side. If it's not, let me know. All right, I don't hear anything, so I'm assuming that you were all able to get to this point. So first concept that was important today that is not related to Precision Ag specifically, it's related to data in general, is to create subfolders for data, code, and output for every single analysis you do, so you keep yourself organized. It's going to be very easy for you to start creating so many files that you lose track of things. And so at least having those 3 subfolders will help you to navigate your own analysis. All right. The next concept I want to introduce to you all is the concept of an RStudio project. This is another very important concept that's going to come in handy in a couple of different ways. So what is an RStudio project? If I just launch any RStudio that I have here, so I'm just going to launch one, like an RStudio window, doesn't have to be specifically with any scripts or anything, just launch RStudio. All right, so here's mine. Let me close this project just so we can see on my side something similar to what you're seeing on our side. All right, so in RStudio, there is this option of creating an RStudio project. Right now, we have not worked with RStudio projects yet. This is the first time you're going to be seeing, at least through this class, what I mean by that. You know that you are not using an RStudio project because on the top right, it says project none. This is how you know you're not in a project, okay? Before I show you how to create a project and we create that for our 02 wrangling exercise, I want to show you why projects are so helpful, especially the more data you have, the more complexity you have, the more this is going to be helpful to you. So if I just click here on my project none, it shows me some of the latest projects that I've worked with here on my computer. So you don't have this. If you never worked with RStudio, you probably don't even have anything here showing up because you don't have previous projects. I'm going to click in one of them. So for example, I was working on a analysis, creating some figures for a book chapter that I just submitted last week. So if I click here, it's going to launch that project for me. Let me just show you how you know you are in a project and what's the difference. All right, so as you may be seeing now, it is showing on the top right a name, which was the name that I gave this project, was analysis 2. So I know I am in a project because it's not saying project none as it was before. So I am in a project. All right. What is the main benefit of working with RStudio projects? If I come here on the Files tab, it's gonna show me this R blue button option, which if I click on it, is gonna show me the folder of this project. Notice how this folder in my computer, I have a folder for code, a subfolder for data, a subfolder for output. If I go inside of these folders, I just went inside code, you see a whole bunch of scripts that I used. If I go in data, you're gonna see raw and processed data in different ways. If I go on output, you're gonna see all the figures I created for this project specifically, right? This is a project in my computer where I'm just gonna open this folder in my operating system so you can see. It's just a regular folder like any. It has the code data and output subfolders with a lot of files in them. And I know it has an RStudio project because at the level of these subfolders, I have this rproj file type, which is what determines an R project. So let's say that, the reviewers come back on the book chapter, they want my figures to be changed. I need to change something about my figures. I just go on my computer and I launch this RStudio project. It brings me directly to the view and the focus of the files of this project, right? I see right off the bat the scripts that I've used here, the data that I'm using, and the output that I generate, all here on this view. Okay, so let's say that happens. I'm working here with this data, with this file. I fix the figure that reviewers asked for me to fix, the map that they asked me to change, and now I want to go back to another analysis that has nothing to do with this. It's another thing from a different project, a paper that I'm working on. I can come here. So, I mean, here is just showing me the most recent projects, but you can really launch a project that even if it's not here, right? As long as you have that rproj icon, you just double click on that, it launches that project. But let's say that I'm working on a, let's see here, a management zone exercise, that I'm preparing this exercise for this class. So I just go to that RStudio project. It's gonna launch a whole new RStudio window that is gonna be entirely focused on the files of that project. So I'm not gonna see anymore what I was doing before for the book chapter, even though I still have code data and output here on the files, but they are different codes, different data, different outputs, now with a focus on this specific project, which is management zone, right? So using RStudio projects, the benefit is that it allows you to shift your view from one analysis to another, from one project to another very quickly without messing things up. If you do not use RStudio projects, you're just going to be opening scripts in R without any project here. You may have a script from the book chapter. You may have byte side, a script for the management zone exercise, which are two completely different separate things running on the same RStudio instance, which is a recipe for trouble, right? You may be creating similarly named objects in different scripts that belong to different analysis that should not be together to begin with, but you are bringing them together because you're not using RStudio projects. So bottom line is use RStudio projects. For this class, you're going to have to use for your own research. I highly encourage you to do as well to keep yourself organized. If you have to shift focus, you just change to a different project and that does the job for you. Another benefit of that, of using RStudio projects, is the use of relative paths. This is a problem that you're going to face with any software. If you are not using RStudio projects and you want to import a dataset that is in your computer, you're going to have to use an absolute path, which starts at the root of your computer, and probably it's going to be like ~user/your name/disk C/ something until you get your file. That is starting from the root, going to your file. If you use RStudio projects, it's going to allow you to use relative paths, which is basically relative to where the rproj file was created. So if the rproj file was created at the root of this project, this is where the relative path starts. So it's a lot easier and more reproducible to use relative paths than absolute paths. And this is a plus both for importing data, but also for exporting maps, right? Whenever you bring something in or export something out, you have to provide a path on your computer. And using relative paths, which RStudio projects allow you to do, is much easier, better, and more reproducible than using absolute paths. All right. So having said all that, the benefits of using RStudio projects, I hope you are convinced. Let's create our RStudio project for today's exercise. The way we're going to do that, in any RStudio window that you have open, so right now I have a project. Actually, let me close this project just so on my side it looks more similar to your side. So now I don't have any specific project open. It says project none, which is probably how it looks like on your side. I want you to click up there, and then we're going to create new projects. Okay, so project none, new project. It's going to prompt you with this if you want to create a new directory, an existing directory, or version control. In this class, we're going to be choosing existing directory because we have already created the 02_wrangling folder. So existing directory. And now we're going to browse to that folder, wherever that is in your computer. So click on browse, and I want you to find the class folder that we created, or the class folder that you already have, but then on the 02_wrangling folder that we created today. So I'm going to look for that on my side. Yay, teaching 2025 program precision ag, and then 02_wrangling. So I want you to go all the way inside 02_wrangling to the point that you're seeing code, data, and outputs. I do not want you to be at the level of the course folder. So if you are seeing 01 intro, you're in the wrong place. You should go inside 02_wrangling and stop here. I do not want you to go inside code, data, or outputs. At the same level that you're seeing code, data, and outputs, this is where we want to create the RStudio project icon. So if you get to 02_wrangling, stop there and then click open. This is going to create an RStudio project. Well, I click open, it came back to this window. I'm just going to say create project. Right, so it's doing its thing. So now look at what happened. Now I have an RStudio window that says 02_wrangling on the top right, telling me that it's created an RStudio project for me inside of the folder 02_wrangling. If I come here on the bottom right and look at the Files tab, I see the code, data, and output that I created before, and I also see the 02_wrangling.rproj icon that I just created now. A couple of important not shortcuts, but things you need to know to navigate this better. As you're going to realize, this Files tab here is useful if you want to see where you are, if you want to just understand this folder structure of this project. But you probably realize you cannot really, from here, from this view, you cannot really move things around, drag and drop files, right? If you want to do that, you have to do that at the folder level of your computer, not inside RStudio. To do that, there is this blue engine here. If you click on that, it has an option for show folder in new window. So click on that and let's see what happens. So that basically launched this folder on my file operating system. And I see again that I have a code, data, output, and now I have this rproj icon inside of this folder as well, right? Meaning again that you create an RStudio project that is inside of this folder. All right, I'm going to close that. So let's say I'm navigating here. So I am on the main level. Let's say I go inside of code because I want to launch this code. You can actually do that, right? So in our studio, click on the code subfolder, and then click on that script. It's going to launch that script for us. Now, on the Files tab, it is showing me inside of the code subfolder. Let's say I want to go back to see the main folder of this project. You click on this R blue button here, and that takes you to the view of the main folder of this project. So again, the couple tips here. If you want to see the files on your folder operating system, you click on the engine, click on show in new window. That's going to open for you like that. And if you in our you're navigating, or in our studio you're navigating inside and outside folders, you can always click that R blue button that takes you to the home folder of this project. All right, so summarizing what we've done up until now. Let me show here the folder in the window. We created a 0 to wrangling folder at the main level of our course folder. We created subfolders, code data, and output. We copied and pasted the files from the 2025 PPA inside of data for the Excel and inside of code for the script. And then we came on our studio and created a project at this level of the folder. So now we have an RStudio project as part of this. All right, before we start talking about the coding part, I just want to take a moment and ask was everyone able to get to this point? If you were not able, you need to speak up, because if you were not able to get to this point, you're going to run into issues as we start coding. All good, Aman? In Tifton, everybody was able to get to this point?
Yes.
All right. So let's keep moving then. So last class, when we did the intro to R, we talked about, or we did everything that we did using an R script. So a file that the extension was .r. If you remember the .r file, we had code that we were developing, and anytime we needed to add a comment or some written language, like English language, we had to add the hash pound, not hash pound, hashtag, right? Pound or hashtag, yes, thanks so much. The hashtag symbol or the pound symbol in front of it to make a comment. So R would not try to interpret it because he wouldn't be able to, right? So R scripts are the way that we start with R. They are the simplest way of scripting. I use R scripts very rarely these days. I prefer to use something like R Markdown, which is what we're using today. So the R Markdown extension is .rmd. This that you're seeing is an R Markdown file. The reason why I like R Markdowns is because it is considered a literate programming tool. What do I mean by that? Literate programming is when you can, on the same script, on the same file, you can mix code, output, and narrative. So narrative is basically when, if you want to write something, if you want to write a comment, you can do that as you would in Word, for example. You don't have to add a comment. You don't have to add the pound symbol in front of it. So let me walk you through a little bit of this R Markdown file. So every R Markdown file is going to start with something like this. So it has 3 dashes, some information, and 3 dashes. This is called the YAML of the file. So it's spelled like this, YAML. It stands for yet another Markdown language. You don't have to really know that. It's just a little bit of background. Every Markdown file is going to have this. And then you get into the actual file. So here we have the key component of an R Markdown is what we call chunks. This here is a chunk. So a chunk begins with 3 apostrophes, and then a curly bracket. It says what's the language that we're using that chunk, in this case R. You can give it a title. I gave a title of setup for this first chunk, and then just have some options. I'm just saying to not show any messages when we load packages. So this is the first chunk. You can imagine a chunk as being the R console. So this is similar to what you would have here. A chunk has a few options on the top here. So one of them is the play button. So on a chunk, you can still run line by line, like we were doing on an R Markdown, or sorry, on an R script last class. So if I just have my cursor in any of these lines and I push Command Return or Control Enter, it just runs that line by itself, as you're seeing here. But you may also decide to run the whole chunk together, which you can do that by coming to the play button and just hitting play. Now, while the chunk is where you're going to code, if the chunk produces an output, that output's going to show up right below that chunk. If you remember from the R script we used when we produced the plots, the ggplot, the plot appeared here on the plots pane. With an R Markdown file, it's going to appear right below that chunk. So imagine you have a file that you can scroll where you have code output, code output, code output, all throughout that file. Another really good option we have here with an R Markdown file is that you outside of the chunk, that is basically a Word document in the sense that you can just write normally. So I can notice this is a chunk, right? So this is a chunk, but here and here, no chunks. I can come here and write whatever I want, right? So this is a script to do wrangling exercises with. This text, I do not have to add a hashtag in front of it because it's not going to be interpreted by R. Only what's inside of a chunk will be interpreted by R. Notice how inside the chunk, I am still writing some comments and I need to use the hashtag. Outside of the chunk, you can just write whatever. And this is also important because if you want to take notes of what we're doing for your own reference, you can write outside the chunk before or after, doesn't matter. As long as it's outside the chunk, you can write your own text as you wish. All right, another important thing here is heading levels. If you are used to heading levels in Word, where you have title, heading 1, 2, 3, 4, and so on, we have the same thing in an R Markdown file. Now, if you are outside of a chunk, like we are here, a hashtag symbol does not mean comment. It actually means heading levels. And this is really helpful to organize your script. So if you notice here, I have my outline appearing. If you don't have, you can just toggle that outline button on and off. And you can really see the outline very easily, right? I have a setup, I have data wrangling, I have assignment, which is coming at the end of this exercise. So you can really navigate this very easily by using your heading levels. So let's say that inside of setup, I wanted to have another, so setup here is heading level 1. The reason why I know that is because it has one hashtag in front of it. If I wanted to, inside setup, I wanted to have a subheading for loading packages and another one for loading data, which are both part of setup. I could come here, give two hashtag symbols or pound symbols and say, for example, I could write, loading packages, which is what we're doing on this chunk here. And then on the next chunk, we're going to be loading data. So maybe I want to come here, do two hashtags and say reading data. Notice how, so here we are defining as a level 2 heading because we're using two hashtags outside of the chunk. But then here on your outline, that also is indented appropriately within the setup, right? Because setup is level 1, has one hashtag. Loading packages and reading data has two hashtags, so they are a level 2. And you can keep going, right? So 3 hashtags will be a heading level 3, 4 hashtags a heading level 4, and so on. I don't think there's a limit here, but just so you get the idea. All right, so again, our Markdown file is a literate programming file type that allows you to mix on the same file your own narrative, if you want to write like this, with code and with output all in the same file consecutively, which is really, I think it's a really nice way of learning how to program, and also helps you if you're sharing your code with somebody else. It's really easy for them to understand what's going on. All right. Another benefit of using a literate programming file like R Markdown is the option of rendering that file. Now, what do I mean by rendering a file? I don't want to do it with our partial script because this is incomplete, right? We're going to complete this script together in class. But I want to encourage you to create a brand new R Markdown file. So if you come here on the plus sign, click there and click on R Markdown. It's going to ask you a few options like what the title you want to give it, what default output format. You can just leave untitled and just leave HTML as your output format and click OK, because we really don't care much about that. I just want to show you what happens when we render it. So you see here the YAML of this file has a title, has output format, and has the date. It has a chunk here that is just setting some options. If you run it, I don't think it even has any outputs. It has a level 2 heading with some text and a link. And then it has a chunk here that uses the summary function that we saw before on a data frame called cars, which ships by default with R. So if you just run that chunk, it just gives you a quick summary. It has another level 2 heading, and then it has a plot. Very simple. I did not do any of this. This is all by default from R when you open a new RStudio file. What I want to show you is on R Mark. So this does not happen with R scripts. It happens with R Markdown, and it happens with Quarto files, which is what we're going to see on the next class. But with R Markdown, you have this option of knitting this file. What does that mean? Knitting or rendering an R Markdown file, it means that R behind the scenes, or RStudio and some packages behind the scenes, are going to transform your script into an output. That output could be HTML, could be PDF, could be Word. This may be useful if you're trying to share with somebody that does not know R or does not have R installed. You want to share with them the results of your analysis. They're not going to be able to run themselves, but they're going to be able to see what code you used, what comments you made, what outputs you generated. So if you click on that knit button, well, we have to save this file first. So we can go inside of code and just save as untitled.rmd. That should be sufficient. So you save there, and I think it's already knitting, or at least on my side, it is already knitting or rendering. All right, it finished rendering, which because it was a very simple short script, and then it gave us this viewer here. If you expand this by clicking on that button right there, this output is HTML, so maybe it's going to open on our browser. And this is what I see. Untitled, a date, I see a heading level 1, I see some text with a link here, I see the code right here, I see the output of that code, I see another heading level 2, some text, and then here, if we go back to the file, we're going to see that that chunk that created this plot had an option to hide the code and just show the output, but it's still showing the plot here. All right, so this here is an HTML file. You could have exported or could have rendered as a Word or as a PDF. It will look the same, and you could share this with somebody. So R Markdown files and Quarto files, which again is what we're going to use next, have this option that as long as you make sure that your script does not have any errors. So when you run the whole script, it runs smoothly without errors, you will be able to render your full script into something like this, and then you can share with somebody. So it gives you a very easy reporting tool as well that R scripts by themselves do not. All right. I want to go back to our RStudio 0 to wrangling. So if you see, notice that this RStudio window says 0 to wrangling below it because it's that project that we were working with. We can just go back there. I'm going to close untitled RMD. I really don't care about it. I just wanted to show you the rendering capacity that it has. You can just go ahead and close that. And on the viewer, if you don't want to be distracted, you can just close on this X button, and that will close that for you. All right, we talked about a lot of things that are going to be key for you to be able to organize your projects, your files, and your scripts. Before we get into the coding exercise of today, which is data wrangling, anybody has any thoughts or questions that we can address?
I have a question. What if maybe you can you copy this code and also like somebody like you give us the option for the need function. Can do you have any option to use this code and somebody can help us to revise them? Maybe you're cooperating somebody.
Yeah, so let's say, Polly, so if you, let's say that you're doing an analysis and you want to share what you found with me, with your advisor.
Yes.
You could do that by rendering, right? That would be an option. Especially let's say if your advisor does not use R, which is not my case, but let's say yours doesn't, and maybe they really don't care about, maybe they don't care about the code itself. Maybe they're not going to be able to help you with the code, but you want to show them like the outputs, right? You could render your file, your R Markdown file, hide all the code, which there is an option that we can choose here to basically hide all the code in the script and just show the output, and you can share that with them, right? So it would almost be like, so if you think about it, you could create reports by doing all of your analysis in R, exporting your figures as PNG, and then copying and pasting those figures into a Word file, and then writing a report, right? Probably everyone has done something like that before. This would be an option where you do not have to leave R Studio to do a report. You can just do a report from R Studio where you have the choice of deciding if you want to show or not your code, show your output, show your narrative around the chunks. I know some people that fully write papers from R Markdown. Like there are ways that you can include citations, there are ways you can include tables, you can format tables. There's a whole world of formatting within R Markdown and Quarto files that some people just publish papers right straight of a Quarto or R Markdown file. They never use Word. Just so you get some idea of how powerful it is.
Yeah.
So yes. However, the thing is, for it to render, you cannot have chunks that don't run because maybe you have like code that's not working or maybe an analysis is not working right and then stops there. So if you have code that's not working, when the rendering process gets that chunk and it gets an error, it's going to stop rendering right there. So it's not the best tool for you to solve coding problems. Let's say if you needed my help to solve a coding problem, you would not render it because it would not render, basically, right? Awesome. Thanks, Polly. Any other questions or thoughts?
Another question about the chunks. What if maybe you wrote like a very long chunk and when you run the whole chunk, it has an error? Does it show you like which line has an error or bug or something?
So when you're rendering, it will show you, but it's not the easiest, it's not the most useful error message, to tell the truth. So what I do normally is if, let's say, if I'm developing a report in R Markdown or Quarto, and I'm getting ready to render, I first try to render. If it does not work because a chunk didn't work, I go back to the script and I try to run each chunk individually. So let's say this chunk here, which right now is incomplete. So I would expect to give me an error because we have not completed yet. But let's say if it was already complete and for some reason I forgot to complete this chunk specifically, if I run it right now, I get an error. You see, it says object soy K not found. So I would basically go to my script and run chunk by chunk and see which chunk gives me an error and then address that error and then try to render again. Awesome. All right, so let's get to our exercise. So again, today we're going to be doing data wrangling or data manipulation. I guess you can also say it that way. I left here, so every script that I do in R, and I think this is pretty common, a pretty common behavior that people do when coding is one of the first parts of the script is going to be what packages you need to use for the whole script. So as you're developing the script, let's say in the middle of the script, you realize, oh, I need a function X from package Y. You go all the way back to the first chunk, load that package there using the library function, and then return to where you need it. So you have all of your library functions on the first chunk of your script. This is pretty common to see. So here we're going to use a package called readXL to read Excel files. Janitor, which is going to help us to clean the column names of our data. Dplyr and tidyr for wrangling, and then readr to export a CSV. I don't remember now if I asked you to install all these packages on that first script you downloaded before the first class. In case you don't have one of these packages, you already know how to install. You just use the install.packages function and then the name of the package, right? So how do I know if I already have this package or not? So if I just have my cursor in the first row right there on the read Excel, and I just hit command return, it's gonna run only read Excel. If I did not get an error below, it's because it's working. I already have it. And I just do that one by one, making sure that they all go through. If you don't have any of them installed, it will yell at you saying that this package was not found or something like that. So then you know what you have to do. Install.packages, name of the package in quotation marks. Remember that if you do install something, you do not want to keep that install.packages function in your scripts. Remember that we only install once. If you leave it here, it will install every single time you run this chunk. So you can type here install.packages if you need to. Let's say I did not have read Excel. You can run this now, but after it goes through and it is installed, either comment it off with a pound sign, or even just delete this from your scripts, because you're not going to need that again. All right, assuming that you all were able to install these packages, that if you hit the play button on the script, it just goes through without giving you any errors. You loaded all the packages you need for this exercise. I'm assuming you all got to that point. If you did not get to that point, let me know, because you're not going to be able to run the following of the script. All right. So the second thing that we normally do in scripts is after we load all the packages, then we bring in the data we're going to be using. I want to read in this data set, so I'm going to come here on the Files tab. I'm going to click on the R blue button to go to the home folder of this project, where I see code data and outputs. I want to go inside data, and I just want to click on the 01 soybeans XLSX, just so we can kind of see it. It is an Excel file. It's not very big. It's not very complex. We'll talk more about its contents in a second, but it is an Excel file. Every time we're reading a file into R, we're going to use a function that it follows the structure of. The name of the function starts with read, and then either a dot or an underscore, and then the file type. In this case here, I want to import this data and assign that to an object called soyk. So I already left you soyk there. You don't have to change that. Just let's give it the assignment symbol, if you remember the less than dash. And then we're going to call a function that the name is read underscore Excel. This function comes from the read Excel package. So if you did not install or did not load the function, then you would not going to be able to see that function in your RStudio. Inside of this function, you just open and close quotation marks. Okay, so the script that we're working with, this 0114 data wrangling partial, is inside the data folder, or I'm sorry, inside the code folder, right? So it's inside of the code folder. Our data is inside the data folder. When I open and close quotation marks, if you have your cursor blinking in between and you hit tab, it's gonna show you the contents, the file contents of where the script is. So right now it's showing me these three options. How do I get to the data in the data that I need? So imagine again, the script is inside of the code folder. I need to get outside of the code folder where I can see all the folders, go inside data, and then call the Excel file. every time you're specifying a path, so this is a relative path, for you to get outside of a folder, for you to go one level up, you can type ../. If you type that and nothing appeared, you can hit tab after that. It's going to show you the contents of where it is. So now ../, basically took us outside of the code folder, and now it's showing us everything on the main folder of the project. Now you can just click on the data folder, hit tab again. It's going to autocomplete with the soybeans XLSX because it's the only file there. If there were 2 or more files in the data folder, it would show you a list of the files and you could choose which one you wanted to bring. All right. So if you were able, and notice something very important here, and I see this mistake a lot. If you were not able to create the subfolders, to create the RStudio project at the right level, to put the files in the right subfolders, if at one of those steps you didn't do like I showed, this path that is showing on my screen will not work on your side. However, if you follow everything that we went through up until this point, this path should have worked. And the way that you know that it worked is now if you run this line of code, you should see soyk pop up on your environment. I want to take a quick moment here because if you had any issues that kept you from importing soyk, we need to address that now. Otherwise, you're not going to be able to follow the exercise. Aman, all good? In Tifton, anyone needs help? All right. I don't hear anything, so I'm assuming you were all able to import soyk like I was. All right, so let's first, I left you here the code already, so we just want to print soyk under this chunk, right? So just run that soyk there. It's going to print the data set for you. Notice how we printed below the chunk, right? This is what I mean by chunk and output, chunk and output. Right below the chunk is appearing just the output from that chunk. So we see here that this is a table. It has 16 rows and 8 columns. You can navigate the rows by flipping the 1 and 2 here. You can navigate the columns by clicking on this arrow here. Another way that is not within the chunk, but let's say if you wanted to take a broader look at the entire data set, there is a function called view. So if you type view, I think that V can be either uppercase or lowercase in this situation. Not every function is like that. If you remember, R is case sensitive. So view soyk, and you run that. Let me show you again. I typed view soyk, and you run it. It's going to pop a new tab here for you that just contains this data frame. All right, so let's quickly go through this data frame and what it has. So this was a study. This data frame is coming from a study where soybean, so the goal here was to assess the effect of potassium fertilizer rates on soybeans, potassium leaf concentration. Okay, so if you see here, we have plot number, we have treatment number, we have stage. So this was all done at the R4 stage in soybeans. We have potassium rate in pounds per acre. And then we have 4 columns with actual data. So we have Tifton, potassium concentration as percentage, Midville, same thing, Watkinsville, same thing, Macon, same thing. So imagine this was a study. It was conducted in 4 locations where at all locations, they had the same treatments of different potassium rates that were 0, 50, 100, 150 pounds of potassium per acre. And then at the R4 stage, samples were collected from soybean plants and then sent, so leaf samples were collected and then sent to a lab to analyze for potassium concentration. And this is the data that we get, all right? So each study was a randomized complete block design with potassium rate as the only treatment factor with level 0, 50, 100, 150 pounds per acre. Now let's use this function here called glimpse. So glimpse is similar to summary, but it gives us a little bit of a different view. So say glimpse soy K. If we run that, this is what we see. So it tells us how many rows it has, how many columns it has. And then for each of the column, it is column names, it is showing us as a row here. It shows the initial values of that column. And then it's telling us how did R interpret those columns. So plot is double. So if you remember, double is for numeric. Treatment is double. Stage is character. And then everything else is double. Everything else was numeric. The next function that I want to use here is the summary, right? So let's call the summary function on the object soy K. If you remember the summary function, if your column is interpreted as numerical or double, the summary function gives you a statistical summary of the column, right? With minimum, first quantile, median, mean, third quantile, and maximum. I always use this summary function for every single script that I use because it helps me at a quick glance to understand if I have some, you can spot some types of errors using the summary function. If you remember, we talked about this in the first class. So a potassium concentration, we know that is going to be positive number, right? There is no negative concentration. And we know, and this is a percentage, so it cannot be more than 100 to begin with, right? Because it is a percentage, or it shouldn't be. Perhaps it could, but if you're doing the calculations correctly, it would not be more than 100. And if you know a little bit about potassium concentration in plant material, you would know that it would probably not be more than 5%. That's like shooting very high, at least for the plants that we work with most of the time. So we know this number should be somewhere between, could be 0, I guess, depending on the instrument, but it should not be more than 5, right? So, and it should not be negative, and it should definitely not be more than 100%. So summary helps you to take a quick look at those and have a feeling of if you have any data points that were entered by mistake. I don't see anything that pops out to my eye right here. Let's say I had a concentration that was negative, like minus, let's say the minimum for Tifton was -2. It was most likely either a typing problem or a machine problem, right? Maybe the equipment that was doing the measurement went a little bit crazy and gave us a negative concentration. So we can easily catch those even before we do anything with it. And if that was the case, you would go into the data set, check out what happened, see if you had any notes, see if you knew who entered the data, see if you have a printed version of the data set so we could see if the printed version was one number and then when it was typed, it was a different one. Anyways, it could be any different things, but summary helps you to identify those. All right, so I guess before we go to our first data wrangling step, I do want to call your attention to one thing here. If I'm going back to the first or the second chunk, I just want to print soy K again. Notice how the columns were named in Excel. So we have plot with uppercase P. We have treatment with all uppercase. We have stage with lowercase everything. We have K rate where we have white spaces and we have parentheses in a column name. This is asking for disaster. Programming languages do not like special characters. Programming languages do not like white spaces, do not like parentheses or other special characters like this. And so you can really see that there's a lot of, there's no default method that was used when naming these columns. And beyond that, there's white space, there's special characters like parentheses. This is going to be an issue as we start coding, and I don't want that to be an issue. One solution is we could go back to the Excel and rename them all manually by maybe including underscores where we have white spaces and then removing the parentheses. We could do that manually. This is a pretty simple data frame. We only have 8 columns. What if you have 200 columns? Then it's not as easy to do manually, right? You just have too many columns for you to go through each one of them and spend a whole afternoon doing something that a function from the janitor package could have helped you in a second. So that's the first thing I want to show you. And this is normally one of the first things I do in my data sets if the column names are like this. They're not standardized. So if you come here to the first chunk, I want to create a new object called soyk_1. So this is going to be our first step of wrangling. I want to give it the assignment symbol, and I'm going to call the function clean_names from the janitor package. And inside of it, we just provide soyk. So notice that on this first step, we're starting with soyk, cleaning the names, and then assigning the result to soyk1. If you run this, soyk1 pops up on your environment, and then if you print soyk1, this is what we see. So the function clean names has a whole bunch of rules that it applies to your column names to make them all standardized. So first thing you should notice here is that everything now is lowercase. This is very useful. So when you are programming and you have columns that have the first letter as uppercase, for example, which is common. I do that a lot still in my programming scripts. All it does for you when you're programming is just adds a couple clicks on the caps lock keyboard key, right? Which when you're programming, you don't need that. Of course, it's not easy to do caps lock on and off, but if you can avoid that, having everything lowercase is just going to speed up your programming. So the default of clean names is to make everything lowercase, as you're seeing here. Every time it sees a white space, it adds a underscore. Every time it sees a special character, it removes that. So notice now that everything is lowercase. Everywhere we had a white space, now it's underscore, and we don't have anymore the parentheses around pounds per acre. Apply that to all the column names, right? Easy. So very useful function to get all of your column names to a standardized state. All right, so let's, yes, somebody had a question? No? All right, if anyone has questions, feel free to speak up. And I'll try to give like silent moments from my side to allow for that. But even if I'm speaking, feel free to interrupt me and ask a question. Okay, so now let's say I want to filter. I want to filter this data frame here, this soyk1. I want to filter and only keep the rows of data where potassium rate equals to 0. I'm just making up a situation here, right? I have no specific reason for that. I'm just creating a case, I guess, where I want to filter all potassium rates equal to 0 and look into just that subset of our data frame. One useful thing that I found is when you're doing data wrangling, you're going to be referring to column names to do things, right? Whenever you're referring to column names, it may be useful to call this function here that is called names, and then you give here soyk1. Don't forget that now we're working with soyk1, not just soyk anymore. And that is going to return you all the column names on this data set. So it's easy for you to copy and paste if you wish. All right, so let's say that on soyk2, I want to only keep the rows of soyk1 where potassium rate equals to 0. Let's go ahead and use the assignment symbol. There is a function called filter, where the first thing that we give it is the data frame coming in. The data frame coming in is soyk1. Make sure you do soyk1, not soyk, just soyk, because now their column names are different. I want to give it a comma and break line just to make it more readable. And now we give a condition. So my condition that I'm telling you is I want to only keep the rows where potassium rate equals to 0. So we can come here and copy the K rate pound per acre. That's the name of the column in soyk1. And you need to give two equal signs. So equal sign, and then a value of that column. So I'm saying from soyk1, just keep the rows where potassium rate is equal to 0. If you run that, and then you print soyk2, we should only have 4 rows. So we have 4 rows and 8 columns. So we kept all the columns, but just the 4 rows where potassium rate was equal to 0, exactly as we asked. This filter function is one of the most useful that you're going to be using a lot of times. So that's why I'm showing you here are the most useful functions that we'll be using throughout the semester, and hopefully most likely for your research as well. So filter is one of those very, very useful functions. You could include here more complex filtering rules. It could be like only potassium rate equals to 0 and plot number equals to 105. So 2 conditions, right? Or maybe you want to have a condition or another condition. There's a whole bunch of Boolean operators we can use here. Let's say an easy one to show is, let's say I want all potassium rates except 0. The way we would change this code is on that first equal sign, you replace that by a exclamation point. So exclamation point equal means different. So all potassium rates different than 0. If you run that and you print soy K, you're going to see you have 12 rows where potassium rate equals to 0 is not there. So Boolean operators of equal, different, greater than, less than, all things of that sort are all things you can specify here on this filter. I'm going to keep equals to 0 just because that was the original script, but I wanted to show you another method of doing the different rather than equal to. All right, so let's go to our next chunk. So soy K3. In R, every time you want to create a new column in that data set, you're going to use the function called mutate. It may not be the most intuitive name for creating a new column, but that's the name of the function, and you're going to get used to it pretty quickly because it's, again, another one of those very, very frequently used functions that we'll see in R. So let's say that my goal here in this next chunk is to create, so if you notice, potassium rate is in pounds per acre. Let's say that this is my study. I'm going to present a poster, and it's a conference where I have to use international units. I cannot use pound per acre. It has to be kilograms per hectare. On the soy K3 chunk, my goal is to do exactly that, is to create a new column where I want to transform my potassium rates from pounds per acre to kilograms per hectare. Let's do that next. So if you come here on soy K3, so I just realized my font size was not the largest, so I just increase that a little bit. So if you come to soy K3, let's give it the assignment symbol. We're going to use the function mutate. The first argument, I mean, 99% of the time, the first argument of functions in R are the data frame or the object coming in. In this case here, I do not want to use soy K2 because it was just an example on how to filter. But I do want to use soy K1 as the incoming data frame because it has the names cleaned already. So let's say soy K_1, which has all the rows and with the column names fixed. Let's give it a break line here. So now the next thing that we give it is the name of the new column. So the column that does not exist yet, the one that we're creating on this data frame. I want to call that K_rate_KGHA. So potassium rate in kilograms per hectare. That column is going to basically be the result. So we give one equal sign. Notice that we give one equal sign in situations for arguments like this is, and we give two equal signs when it is a Boolean operator, when we're trying to differentiate things, equal to, different than, greater than, lower than, right? So Boolean operators, two equal sign. If it's just an argument, is a single equal sign. So this column here is basically going to be a transformation of the potassium pounds per acre column, right? So if you just go back above, you can copy this name, K potassium rate pound per acre. So to transform from pound per acre to kilograms per hectare, we multiply that, the pound per acre rate, by 0.454 and divided by 0.405. This is the conversion factor from pounds per acre to kilograms per hectare. Make sure you have first here is potassium rate pounds per acre times with asterisk this number and then divided by this other number. I'm going to give you a quick second here to catch up in case you need to. All right, let's keep moving. If you run this and if you had your commas in the right place, if you had your closing parentheses in the right place, it should run smoothly. And then if you print soy K3, you should still have 16 rows, right? We did not affect rows. We just have one extra column. So we went from 8 to 9 columns. And if you use the arrow here, you're going to go to the last column. This is our potassium rate in kilograms per hectare. And it's a numerical variable. It's a DBL. It's a double variable. If you notice, I mean, it did the conversion for us, but it has way too many decimal points. We really do not need that, right? Imagine you're going to show this in a plot. Maybe on the x-axis, you have potassium rate in kilograms per hectare. You do not want to show this huge number. Just 0, 56, 112 is going to be enough for us. So let's round this up to no decimal points. To do that, you come back here to the after the 405, give it a comma and hit return. We're basically gonna call again the same column name, potassium rate, kilograms per hectare. I'm just gonna copy and paste. So we're going to basically overwrite. We first do the transformation and then we're overwriting. So potassium rate, kilograms per hectare, one equal sign. We're gonna use a function called round. Inside of this function, you give what column you're rounding, which again is the same, right? So potassium rate kilograms per hectare, that's the column you want to round. You give it a comma, and the next argument is how many decimal points. I want 0 decimal points. So let's put just 0 there. Make sure you have one parenthesis closing the round function, but you still need another parenthesis in the end closing the mutate. And if you have too many parentheses, you get an error as well. So make sure you have correct parentheses, no more than that, no less than that. All right, if you run it and you print it, and you go all the way to the right, you have your potassium rate in kilograms per hectare without any decimal points, looking very sharp, looking really good. That's all that we wanted. All right. Okay, so a lot of data wrangling is really to get your data to the correct shape and format for you to do analysis. This was a randomized complete block design, which means that we need to have the block information as a column. Let me print again soy K3, which is our latest version. And I want to have you all help me here. I don't think I'm going to be able to show all columns at the same time. Well, let me use the view just to make it easier to see everything. View soy K3. And let me get my face out of the way. All right, so this is our data frame right now. If you look at the columns, we do not have a column with block or wrap information. But we need that. We need to have that because on the modeling function, we need to say what is the block for this design. If you already watched my videos before and you know the answer, I would ask you to not answer right now. But if you're new to this content, I want to ask you, how can we retrieve block information from what we have right in front of us? Any thoughts? Let me go to Tifton and pick on some brains on that campus. So of those in Tifton, anyone has any thoughts on how can we use the current data to extract block information? I cannot fully see who is there, but I'm gonna call a name. I think Luke is there, right? Hey, Luke, any thoughts here? What do you think? And you're all muted, just to let you know, in case you are speaking, I'm not hearing you.
I can go ahead and try and answer. Benedetto also had an answer, but I can go. So by extracting block information, you just mean separating this data into like the blocks, but you mean the potassium application rate?
No, so the potassium application rate is the treatment, right?
Right.
And but these treatments were randomized in blocks, in replications. So, and maybe, sorry, I was not hearing you all in case somebody else spoke up, but did Benedetta say something as well?
No, it probably is wrong. So no.
Oh, no, go ahead and say, I mean, we're all learning here.
Like, I don't know if it's correct, but I know that there was a function that was a corpate or something like that, that associate the one column with another.
Okay, so I guess so you're thinking in a step maybe that's after what we're trying to answer now, which is if you look at these columns, which one of these columns would help you to know what block that information came from?
The ERT.
Can you say that again?
Treatment on stage.
Okay, so not exactly. So here's, and maybe, and I don't know, this probably depends on how much experience you have working with field research as well, or even lab research, but using plots, right? So normally,
Yes.
and this doesn't happen always, but normally your plot numbers are numbered according to the block. So let's say on block 1, your plots are 101, 102, 103, 104, 105. On block 2, your plots are 201, 202, 203, and so on. Right? So if we were handed this data set, which does not have block information, and assuming this is how people number their plots, we could extract the block information from the plot number. Right? Does that make sense? I mean, has anyone seen this in your research where your plots were numbered, like the first number of the plot is related to the block where it was? Have you guys? Yeah.
Yes.
Right. Awesome. So that's kind of that's the rationale I'm trying to get to you here is we don't have block information yet, but we need that column. We need to have a column saying block or rep and saying 1, 2, 3, or 4. We can kind of guess, I mean, we can guess that information from the plot number, and that's what we're going to do next. So let me close SoyK and SoyK3. Thanks for those that helped, Benedetta and Luke. All right, so let's go to SoyK4. If you use Excel for your data manipulation, you probably have used an if-else statement, which basically means if a given condition is true, then this happens. If that condition is false, then that happens. That's basically what an if-else is. We have if-else functions in R as well, but when you have more than 2 conditions, if you're using if-else, it becomes very difficult to read because you're nesting conditions, you're nesting if-else inside of if-elses, and then it becomes very hard for humans to read that code and make sense. In R and in dplyr, there is a function that solves that issue that is called case when, and that's what we're going to use here. So if you come to SoyK4, let's give it the assignment symbol. So my goal is to create another column that's going to be called rep for replication or block, but we can call it rep. And on that wrap column, I wanted to have the information of the block. So 1, 2, 3, or 4. Because we're creating a new column, I hope that you thought we needed the function mutate. We're creating a new column, we need mutate. So can type with me mutate. If you remember, the first argument of 99% of the functions is the incoming data set. The incoming data set is soy K3, you can just type there. We give it a comma. I want a break line just to make it more readable for us. And then we give the name of the new column that we want to create. The new column, I want it to be called rep. It could have been called block. It could have been called something else. I just decided to name it rep. So rep equals to, and then here we're going to specify 4 conditions. Before we start specifying those conditions, we need to have those conditions inside of this function case when, because it's going to help us to write those conditions in a more readable format. So right after the equal sign, call case when. It's going to open and close parentheses. With our cursor in between the parentheses, break line again to make it more readable. All right, so if my assumption here is that all the 100s plots with a 100 numbering are coming from block 1. Plots with 200s, block 2, 300s, block 3, 400s, block 4. That is my assumption coming in. So we're going to need to use the column called plot, right? We have this column above. Let me print again soy K3 above just so we can see. We have a column called plot. It is numerical, and it has all these numbers with 1, 2, 3, and 400s. So if I come back to case when, my first condition here is going to be if plot is greater than 100. So you say the condition and then you use the tilde to say then. So if the value under the column plot is greater than 100, then I want wrap to be 1. Oops, sorry, 1. Okay. And then for now, I just wanna, let's see if this even runs. Oh, soy K not found. Oh, I'm missing an underscore. Notice how I forgot an underscore here before the 3, and R says, I don't know what that is, right? So R is very sensitive. I mean, any programming language is case sensitive, but also we have to specify things exactly as they are. All right, so let me try to run this now. It did run, it went through. Now I want to print soy K. So really I want to pay attention to the plot column. Let me use the view of soy K4 just so it's easier for us to see everything in one tab. All right, so notice what happened. I said if plot is greater than 100, then wrap should receive the value 1. Well, to begin with, I did not specify what would happen if plot is greater than other numbers like 200 and 300 and so on. So I would kind of expect that I would get, a handful of ones here. But what is the problem on my rule here? If I say this, I mean, what I want is that plots that are 100, so 105, 102, 106, I want those plots to be 1. But maybe everything else should be an A at this point because I have not specified the other conditions yet. So why is everything 1?
I think that it's because of the great sign. So if the number is greater than 100, will be 1. So the limit is not set. So it will continue to be 1.
Perfect. Thanks, Polly. That's exactly right. I established the lower boundary of the limit, but all the numbers under that column are greater than 100, right? So for this condition, I should establish the upper limit of that condition as well. So I should say if plot is more than 100 and you need to use this and sign, plot is less than 200, then block is 1, wrap is 1. Right? So I established the lower and upper limit of my condition. If you run this and you print soy K4, or let me actually use the view again. Okay, so now we happen what we were expecting. So all the hundreds now have a rep 1, and everything else is just NA because it did not fall into that condition, right? All right. So now we provided the first condition. Now we need to continue doing this for the other conditions. So now that you kind of got the idea of how this works, I want to ask someone in Tifton to help me to create the rule for block 2. So let's add the comma here. I want to break line so it's more readable. And then I want to ask somebody in Tifton, except Polly, at this point, Polly, for how would you write the condition for the block number 2?
Block higher than 2 and lower than 3.
Yes, was that Benedetta?
Yes.
Awesome, thanks, Benedetta. Yes, that's exactly right. So we would say if plot is greater than 200 and plot is lower than 300, then, and the then is specified with the tilde, 2. So we're basically saying if plot is more than 200 and less than 300, then rep equals to 2, right? This 2 here is associated with the rep, not with the plot, right? So if you go ahead and run this and we do the view soy K4, that is exactly what's happening, right? So all the 200s now have a rep equals to 2. All the hundreds is rep equals to 1. And we still have NAs for reps for the plots with numbers 300s and 400s, which we're going to address next. All right, so I'm just gonna type it out with you here. I'm not gonna ask anyone specific this next step because I think you were all able to get it, but you just make sure you add a comma there. Let's say if plot is more than 300 and plot is less than 400, then 3. Add another comma, hit return so it's more readable. And then lastly, because 400s are the highest level, we don't have a block 5, we don't have 500s. I'm just gonna say if plot is greater than 400, then rep equals 4. So all these 4 conditions that we specified inside of the case when, inside of the mutate. So remember, mutate creates a new column, incoming data set soy K3, rep is the name of the new column. We use case when because we're specifying more than 2 conditions. We specified 4 conditions here. Case when helps us to make the specification more human readable. That's why we're using case when. So if you run all that, if you had your greater than and lower than, and you had your and signs, and you had your commas at the end, you had your tildes correctly, this should all run well. And then soy K, if you print soy K and you go all the way to the right, it should have rep 1, 2, 3, 4, 1, 2, 3, 4. And if you were to compare that with plot number, it would follow the condition that we established. Awesome. Any questions? Right, I don't hear any. So we can keep moving. Let me see, our class goes until 4, right? Is that right?
Yes.
Yes, until 4. Okay, so maybe we can do one more chunk here and then we'll call it good. All right, so the next function that I want to show you is the following. So if we look at soy K4, and if let's say that we want to run this analysis, imagine a model where I want to have the location effect. If I want to include a location effect in my model, I need to have a column that let's say is called location. And under that column, I would have Tifton, Midville, Macon, Watkinsville, right? I do not have that at this point. Where is our location information right now? Where is that located in our data set?
The first row, the title row.
The title of the column, right? The column names. So
Yeah.
Midville, Watkinsville, Macon, and Tifton are on the column titles. And that is useless if I want to include location in a model or even in a plot, right? We talked about using ggplot on the intro to R, where we color by favorite crop. What if we wanted to color by location? I have to have a column that says location or something like that, where we have location names under it. We do not have that right now. That information is on the column heading. This is a common thing to happen depending on how your data is recorded on the field, how you type that into a computer. You may have important information on your column headings, where if they're there, they're basically useless for you to use that in plotting or maybe in modeling. So we're gonna use, what we have to do is we're gonna pivot longer. What does that mean? So pivot longer is gonna take these 4 columns with location, and right now they are on a wide format. They're going horizontally. I wanna take those 4 columns and I wanna stack them below each other. So for that, we're gonna need 2 new columns. One new column is gonna be called something like column name or something like that. We're gonna make something up here on our exercise. But that column is basically gonna have the current column names. So imagine we take Tifton here, it's just Tifton. When we pivot longer, all the values under Tifton are gonna go into a new column called value. But then I need to specify that these values are coming from Tifton. So I need another column that is going to repeat Tifton KPCT for all these values. And then I do the same for Midville and Watkinsville and Macon. So I take all the values of those columns and stack them below each other. But now I need to differentiate which values are coming from where. So I need a new column that is going to repeat Tifton, 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 Watkinsville, Watsonville, Macon, 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 and so on. So that's what pivot longer is. We're making this data from wide to a long format. That's what pivot longer does for us. So we're gonna do that next. So if you come here on SoyK, you give it the assignment symbol. We're gonna use a function called pivot underscore longer. As always, the first argument is the data frame coming in. That is SoyK4, is the one that we just did above, where we created the wrap column, right? So SoyK4 is the incoming data set. Give it a comma. Pivot longer has many different arguments, but the minimum required that we have to specify is one that the first one is going to be called names2. So this is where we give the name of the new column that is going to contain the current column names. I want to call this open and close quotation marks. I want to call location.k. So on the new column where the names Tifton, Watkinsville, Macon, and all that's going to be located, it's going to be location.k. Give it a comma. I want to give the name of the column where the values will end up at. So we call values2 is the name of the argument, and I want to call that column k underscore PCT. And now if we just run this, let's see if it even runs. Okay, it did not run because it gave us an error saying that we must select at least one column to pivot longer. So we have not specified yet which columns we want to pivot longer. So let's give it a comma. The argument for that is called cols or columns. So I could come here, use the C function and specify the name Tifton KPCT, Midville KPCT, and so on. There are different ways we could do this really, but I just want to show you a new trick here. Because the columns we want to pivot longer all have the KPCT in the title. So Tifton KPCT, Midville KPCT, Watkinsville, and Macon KPCT. All of them contain that KPCT, and no other column that we don't want to pivot longer, no other column has KPCT except the 4 we want to pivot longer. So we can come here on the cols and we can use a function called contains. So I want to select the columns that contains in quotation marks k underscore PCT. So this is basically saying all columns that contain the name or that as part of the name contain the words KPCT, those are the ones I want to select. If you run that and we print it, this is what we get. So let me use a view here, just so it's easier for us to see. So the first thing to notice is we had an initial number of rows of 16. Now we have 64, which is basically 16 times 4, because we pivoted longer 4 columns, right? We stacked 4 columns below each other. So 16 times 4, that's the total number of rows that we have there. I think it was 16, right? Let's see, soy K4. Yeah, it was 16. Soy K4 was 16. Soy K5 has 64. And now notice what happened here. So plot, treatment, stage, potassium rate, all the same. And until rep, right? But now we have a new column called location, where the previous column headings are all here. And then every value that's coming from Tifton says Tifton KPCT. Every value coming from Midville says Midville KPCT, and so on, right? So we have 16 columns per location, but now we have one column where we have the location information. We have one column where we have the concentration of potassium as a percentage on the leaves. Nice. This is getting there. It's not fully 100% there yet, but it's getting there. So this is now we have at least some column that has some information about location that we can use in plotting, in analysis, and so on. All right, I think this is probably a good stopping point for us. So I want to ask you to hit the save button on your script. So click that save button. And then let me take attendance for today. So I want to come here on GitHub. That's where we're going to be taking attendance every time. I was telling the other class that I take attendance through GitHub because I have developed a script that pulls information from GitHub and makes a nice table with who responded, who didn't, and gives me that as attendance. So it's easier on my side. So I'm going to create here a new issue. Oops. Hold on. A new issue. I want to call it attendance January 14th. Make sure you claim your attendance. Just drop me a hi, a hello, I'm here, go dogs, whatever you wish, just so I know that you were in class. And that should be all for today. Oh, I think I stopped sharing. Let me share again. All right, so before we wrap things up, I just want to check if anyone has any questions or issues or anything that you'd like to ask at this time. All right, I don't hear anything, and as long as you claim your attendance, we're good to go. We'll see you on Thursday, where we're going to finish this exercise and maybe we'll start getting to work with some spatial data depending on the time. I think we will. So see you on Thursday.
See you.